All right, applications of integrals to kinematics. We learned in derivatives that if you took the derivatives of your displacement formula, you get velocity. And derivative of velocity gives you acceleration. So putting all together, we get the fancy word sva. And if you wanted to do this with integration, if this way is the derivative, then this way would be integration. So now you could start with any part of those and work forward or backwards to find the other things. So relatively straightforward and nothing too crazy compared to what we've learned in the past with kinematics. Although we will do some, or the last question of this one is a little bit crazy. But we'll ease into that slowly. So what often happens in these questions is you get a starting point. Here, the starting point is with acceleration. They tell us that the acceleration in meters per second squared is t plus 1. We want to find an equation for velocity and an equation for displacement, and we're given some information. So we have some information that when t is 0, v is 8. When t is 0, s is 0. That's going to be in some important information because those are, in a sense, points on those graphs. Starting with our acceleration, if we want to find velocity, working backwards, we'd integrate. So if we integrate t plus 1 with respects to t, then we're going to be able to, so add 1 to the exponent divided by 2 plus c, we're going to be able to find that equation. Yep. So since we know that the velocity at time 0, oh, there we go. Since the velocity at time 0 is 8, we can plug that in. Oops, at time 0, sorry. The velocity at time 0 is 8. We can see that we can solve for c. So now we not only know the equation for the velocity, we know all about it. We know that it's going to be t squared over 2 plus t plus 8. And we have our equation for our velocity. To find our equation for displacement, we can integrate again. Integrate our velocity equation. And again, we go back to the information we were given at the beginning. We were given at the beginning when time was 0, the displacement was 0. So plugging in 0 for t and 0 for s and solving that would give us that d has to be equal to 0 as well. So our final equation for s is t cubed over 6 plus t squared over 2 plus 8t plus 0, or just plus 8t. So what did we do? We took our knowledge of how the derivative of displacement is velocity, the derivative of velocity is acceleration, and since we started with acceleration, we just worked backwards until we found our displacement formula. We integrated along the way. We had to use this information that was given to us at the beginning as we integrated along the way so that we could solve for c and then finally solve for d. This time we're given velocity. So if we think about we're starting in the middle. So we can find displacement by integrating, acceleration by taking the derivative. So find the acceleration. Well, the acceleration will be the derivative. The derivative is easy. It's just going to be -10. Looks like a rounded version of gravity. If the initial displacement is 40 meters, so what does that mean? Initial always is telling us when time is 0. So when time is 0, the displacement is 40. If we want to find S, the way that we could find S is working backwards from velocity, so that's going to be integration. So we would integrate. That's a bad looking 10. 50 minus 10t. And since we know that the initial displacement is 40, plug in 40 for S, 0 in for t, and we get c is equal to 40. So our final equation will be 50t minus 5t squared plus 40. Okay, I'm going to get you to try the next one. It's good. Ready for part B? So once you've got part A, find the displacement. Just integrate again. Again, the initial displacement was 2. So when time is 0, S is 2. What does it mean for something to be at rest? The velocity is 0. So you go to your velocity equation, set it equal to 0. You can factor and solve. And then finally, calculating the displacement at those times. So here we've got when t is 1 and when t is 3. So there's a difference between displacement, because displacement is always compared to where you started from. So for example, if I take a ball, bounce it on the ground, and catch it right back where I threw it from, its displacement is 0. But since I've dropped it, it bounced and then came back up. It's traveled a certain distance. The same distance it went down, it traveled to get back up. Same thing if you throw it up in the air, comes back down. It's traveled a distance, but its displacement is 0. It's probably one of the reasons I don't really like jogging, because you start by going out your front door and you end back at your front door. I could get there a lot faster if I hadn't done anything and just stayed there, because your displacement is 0. So I can see the purpose of, you need to get somewhere. If I wake up at 8:27 and I start teaching a class at 8:30, well then maybe I'll run because I have to get there. But just running for the sake of running, I'm not sure. So there is a difference between displacement and distance. Now if you're calculating that, say your velocity formula, and you want to figure out the distance it travels. So when I threw that ball up in the air, if I would graph this, this being time here, velocity here, I'm going to have an initial velocity, and if it's going upwards, I'm going to call that a positive velocity. So when it goes upwards, I have an initial velocity, but what's happening as I throw it up? Because of gravity, it's slowing down. So that initial velocity is slowing down until the velocity is 0. And at the moment where the golf ball that I threw is at its maximum, and it's stopping and changing direction, that's when its velocity is 0. And then it starts coming back down. Since its direction is coming back down, now its velocity is negative, and so it may look like this. Now, if we integrated, let's say that whole thing took 2 milliseconds, maybe 2 seconds, I don't know. It's hard to count when you throw something up in the air because you're kind of 1, 2. So 2 whatevers is how much time it took. If we integrated this, we would calculate this area and this area. And since one of the areas is below, that area would be negative, and it would cancel out with the area above. And so that's why when we integrate the whole thing, we get our displacement, and we get 0. But if we wanted to calculate the distance it traveled, we're going to need to find this point right here. I'm going to call it A so it matches up with what we have in our formula. And if we want everything to match with our graph, then these absolute values should go away, and we should add them to this one. Because the part that's below is going to be negative. So if I do the absolute value of that, that will change this value here that's negative to a positive, and then you would add both of those distances. And both of those distances together would equal the total distance that it's traveled. Good? So now let's get into some more complicated questions. This first one isn't so bad. The second one is worse. Golf ball is thrown upward with a velocity of 7 meters per second from the edge of a cliff 75 meters high. So we probably need a picture for this. Fancy cliff, some fancy things in the rock. Here you are, sitting with your legs hanging over the edge, smiling, throwing a really big golf ball up in the air. Apparently you have no arms. That's okay. So, an initial velocity of 7 meters per second upwards, so that is our initial velocity. So if we saw what's going to happen with this ball, or golf ball, it's going to go up in the air and then it's going to come back down. So it's going to travel along this path and end up somewhere once it hits the ground. Okay, perfect. So this is what's going to happen. You're probably thinking, if you've taken some physics, I have a ton of physics formulas that I've done questions like this before. So now we're going to say, we don't have those physics formulas. We're going to just do this with calculus. How will that look? How will we solve this? What do we know? We know acceleration. So we can start with the one thing that, in fact, we'll write out everything that we know. From this question, we know that acceleration is negative 9.8 meters per second squared. We know an initial velocity, so we know when time is equal to 0, velocity is equal to 7 meters per second. We know an initial displacement. We know when time is equal to 0, where's the golf ball? And I guess we do have to make a decision what we want our displacement to be in reference to, because we can solve this equation in a bunch of different ways. We can say this is 0 and set up our axes there, or we can set this as 0 and say we're starting 75 meters above. So do you want to start with ground level being 0? So if we start with ground level being 0, then the initial displacement is 75. It's always important in these questions to write out all of the information that you were given, because then you can use that moving forward. From this, I've got an equation for acceleration. So then my velocity will be negative 9.8 dt. And if we integrate that, that's a really easy thing to integrate. We get negative 9.8 t plus c. But since we know that our initial velocity was 7, when we plug in 0 for t, we get that c is equal to 7. So our velocity equation is negative 9.8 t plus 7. Our displacement equation then becomes the integral of that. And so every single quadratic equation that you did growing up, aka 2 years ago in grade 11, every single word problem that you did that had something thrown in the air with height, you can see why in this question that you would always get a negative 4.9 t squared. I mean, I could have done negative 9.9 t squared divided by 2. I just divided the 9.8 divided by 2 already. Is that okay? So you would see, oh, every single question we had either negative 4.9 if it was a calculator or negative 5 if it was not calculator, because they made the number nicer for you. And integrating the 7. You didn't know this at the time, but your initial velocity is always in your displacement. Your initial velocity is always in your displacement formula as what's the coefficient of t, or of the second variable. And then this one would be plus d. Of course, since we're starting 75 meters above the ground when time is 0, displacement 75, so that tells you your d value is 75. And that was one thing you might have recognized. Way back in grade 11. So now we've figured out our displacement formula, we figured out our velocity formula. Why should we figure these things out? What was the question actually asking? How long will it take the golf ball to hit the ground? So we want to find t. What do we know about this moment? The height is equal to 0. So where does that come? In which equation would we put the height equals 0 in? I didn't use any h's. In the s one, right? Because that's our displacement. And if we started, right, we started with our initial displacement 75. So we put 75 right up here. That meant ground level was 0. Okay, we're making some assumptions. We're making some assumptions that there's not another cliff after the first cliff, and this ground is more or less perfectly flat in this question. But with that, yes. So we need our displacement to be 0, and you just have to solve for t. Just eyeballing this. Does this look like one that factors nicely? No? What, the negative 4.9 give that away? Yeah, so this doesn't factor nicely. If you had no calculator, then, oh, I want to keep going in black. You would use your quadratic formula, negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. Yes? And you could just use your calculator, graph it, and find your intercepts as well. What I'm doing with the quadratic formula is if this was non-calculator, okay? Well, if it was non-calculator, there are times where they would allow you to leave an answer somewhat unsimplified like this, okay? So yeah, 4 times 4.9, it's not that hard. Times 75 adds a little bit of calculations, definitely. So you could do this. If we did go to our calculator, because this most likely would be a calculator question, yes, it would be easier to graph this. Negative 4.9x squared plus 7x plus 75. Okay. What do we know about this graph? We knew our cliff was 75 above. So when I'm going to my window, I want to see that cliff. So I'm going to start it up at 80. I mean, it depends how hard. I'll start at 100 so we can see that graph. I don't know how much time it would take. 10 meters per second acceleration. I think 10 seconds. 10 seconds might be enough. If we graph this, we see ourselves sitting on the cliff right here, throwing it up, and it hits the ground there. Now there's 2 x-intercepts, but based on what's happening here, can you see that the only one that makes sense is that positive one? So we want to find that x-intercept, is that 0. Put a value to the left, put a value to the right. Calculate it, and you get 4.7. So it takes about 4.7, 4.69 seconds before it hits the ground. So you could work backwards from this. If you trained yourself, your arms, so you knew how hard you threw it up. I guess it would be easier just to drop it, to have an initial velocity of 0. Then you could just figure out how, count it out till it hits the ground, and then you could work backwards to find out how high above you're going, right? If it's too far, when you drop that rock that you can't hear it hit the ground, then you could just jump off the cliff and count until you hit the ground. Then you know for sure what the time was. And then next 6 months that you're in the hospital, you can do the calculations to figure out how high that cliff was. So this question, besides the final answer that the factoring doesn't work and you'd have to either use a quadratic formula or a graphing calculator, it's not that bad as far as the integration goes. The big thing that this one has that you have to remember, it's not stated anywhere in the question that acceleration is gravity. So that's a fact that you'd have to pull out of this. Any initial reactions to this question? Does it seem complicated? Again, without using any physics formulas, just using calculus. Yes, this is complicated. You've got a specialty car where all you have to do is push a button and it increases its speed at a constant rate. So it accelerates at a constant rate until you reach your speed that you want to get at. Maybe they've done some research. Maybe they've done some research and said, if you accelerate at a constant speed, it's the best for your fuel economy or mileage. So because of that, these new fancy cars have this in place. You just say, I'd like to reach 100 kilometers per hour. Then you can fall asleep and it drives for you. So again, we start off by writing down everything that we know. What do we know? We know some things at time 0. What's our displacement at time 0? 0. Do we know at time 0 our velocity? It's also 0. What else do we know? At time 20, and I'm going to put seconds there, our velocity is 100. And it's important to add our units here because this is going to be the first problem that you'll run into if you did this question and then checked your answer in the back of the book and it was wrong. It's because one time is in second and our speed is in kilometers per hour, and we want to find our total distance in meters. So none of our units jive. Nothing is correct, so we're going to have to deal with that. And what we want to find when the time is 20 seconds, what's our displacement? So this is the information that we've got. We're also given one other piece of information. We're given that we're increasing our speed steadily at the same rate. But we don't know what that rate is. To figure that out, well, we're going to have to do some work. But initially, what we can say is we can say our acceleration is, choose your favorite letter for hard questions when you don't know what it is. C? Oh, I find K. It's like if there's a K in the question, I think it started in grade 9. It's like you had all the easy questions and then there was a question with a K in it.
I've never seen an F.
Yeah, well, that's because Q might be tough. Should we make it harder? Should we make it a Q? Should we? K is fine. Should we go to like some Greek letter? You want to use lambda?
Yes.
You want to use lambda or C? How about that one? Gamma. How do you? That one. Anyways, yeah, we'll go with K. Okay? So we know our acceleration is some number, we just don't know what that is. But at least that gives us a starting point. So I'm going to draw a line, because all of this above the line is what we know. Yes? So if we know this, what do we know about our velocity? Our velocity is going to be our integral with respect to time of our acceleration. So our velocity yes. You want to just use A? We could, because it's acceleration. But the problem with using A is you have your formula acceleration equals, and then you write A again. In one part, acceleration stands for acceleration, and the other part, A stands for a specific number. So it might get a little confusing if we did A equals A. We could use alpha, because it's kind of an A, but kind of not. Can we figure this out? Yes. What can you tell me about C? C is 0, because when T is 0, V is 0, so we can solve that out and find out that C is 0. So then it becomes that our velocity equation is just KT. Can we figure out k now? Do we have enough information to figure out k? Yes. What can we plug in? 20. Okay, 20 and 100? No. You're just kidding. Ha ha. We're just kidding. Why are we just kidding? Because it's a joke. We do have this information here, right? You will be very tempted to use 20 and 100, and it is technically right in the wrong units. So you either need to make your decision. Do you want to deal in, what units do we want to deal in? Meters per second. So then we're going to have to change this velocity. What is this velocity equal to in meters per second? 27.7 repeated? Is that something you've memorized or you've used enough? Or did you figure it out? You did look it up. Oh, you looked it up. You didn't even do the calculations. Oh, okay. So you did do the calculation. Are we all okay with how we would change that? Because 100 kilometers per hour, there's 60 minutes in an hour. So if you divided by 60, you'd find out how many kilometers you went in a minute. And divide by 60 again, you'd find out how many kilometers you went in a second. And then you divide that by, or times that by 1,000 to find out how many meters you would have gone in a second. Okay? So we get 27.7 meters per second. So now, someone tell me a joke that's not funny? Yeah, ha ha. So now we can put our velocity in with the units all being the same. 20 seconds, we're going 27.7 meters per second. Solving for this, does anybody have the exact value of 27.7? Divide that by 20 and tell me what this is as a fraction as opposed to 25 over 18. Perfect. So if you kept all those decimal places and then you divided by 20 and you got a new number that was a big decimal place, you could hit the math fraction button on your calculator and it turns it back into a nice fraction for you. So now we know that our acceleration is 25 over 18 meters per second squared, because those are the units that we're using. And we now know our velocity formula is 25 over 18t. Our displacement formula, because we want to find out how far it goes in 20 seconds, our displacement formula is the integral and again, since the initial displacement was 0 when time was 0, d is equal to 0. And so we get our equation for our displacement is going to be 25 over 36 t squared. Now, to find out after 20 seconds, and I calculated this earlier. You could get 277.8 or 277.7 repeated. And this would be, since we've been using meters and seconds all the way through, this would be in meters. So on a question like this, This is a really hard question because it's hard to start. So it's hard to take the information that you have. Yes?
Well, you could just find it in meters per second and times it by 10.
Find it in meters per second.
That is the answer, 27.7 times 10.
Oh. It works, right? Voodoo math again. Love it. But the hard part is the setup, in this case, saying it's going to be a good idea to start with something that I don't know and write an equation with it. Right? That's a hard starting point, to say my acceleration is k, and then work with that. But because we know that it is going at a constant, it's accelerating steadily, once you have that, then you can go through all of your SPA stuff and integrate backwards and get your velocity. And you had enough information in your velocity then to solve for k. And then from there, find out your displacement formula, and then everything else was easy to calculate. And that's integration. That's our integration unit.